Well, good afternoon, everybody, and welcome to Session A. I hope you've enjoyed your lunch, and we have a very interesting set of talks this afternoon for you. If you're just coming in, please come in, take a seat. My name's Patrick Ryan. I'm a director of Patrick Ryan Associates, and I'm here today to chair this session. Track A, so you are in Track A at the moment, just in case you're wondering. So welcome. We have some great speakers lined up for you, and so without any further ado, I'm going to introduce the first one. And our first speaker this afternoon is Douglas Paul, who's an associate partner at Architects RSHP, and he will be speaking on an inclined triple glazed facade from design concept to completion. So please welcome Douglas Paul.
Thank you, Patrick, for the introduction, and thank you for giving us the opportunity to talk. Yes, so today I'll be focusing on the triple glazed facade for a pier extension at Geneva Airport. Often the most challenging sites lead to the most interesting results. I'll start by explaining how the constraints of the site led to a very specific facade design. So the Canton of Geneva was the last to be admitted into the Swiss Federation, and essentially it forms an enclave. The green area, the green overlay is France, and you can see Geneva is a bridging point where the water from Lake Geneva flows into the Rhone River. The airport, you can see, is close to the... Is this pointer working? It is, sorry, bear with me. Yeah, so there's the airport there. It's close both to the lake and to the city centre down there. And it's essentially at the pinch point between France and the lake. So if we fast forward to the site plan, essentially the footprint of the pier is in blue, the existing terminal in green to your left, and the landside perimeter is in pink. The pier was serving 6 stands which were already in operation. If you'd flown into Geneva prior to the LS being built, you probably arrived at one of 2 satellites out on the apron, and you traveled through a tunnel to the baggage reclaim hall, which is essentially an underground arrival experience. And your main impression of Geneva, initially at least, would be of watch adverts, more than likely. In 2010, Geneva Airport launched an international design competition to select a design consortium to design the pier extension, and this was the reference project. I just want to highlight 2 things about this. First of all, they imagined that there would be in terms of arrival sequence, you'd be entering an underground tunnel that connected into the baggage hall. Another thing is that these large boxes which protrude into the airfield house the vertical circulation stairs and escalators. I should explain, it might be obvious, but on the right is the airfield, on the left is the landside. And in February 2011, RBIT was the design consortium announced as a winner. That consists of Roger Stark Harbour and Partners, Jacques Bougne Architects based in Geneva, the Angerop engineering group based in Paris, and T Ingénierie, which was a structural and civil engineer based in Geneva. And essentially, one of the key aspects that RBIT won was that we placed the arrival sequence above ground. So the orange zone is the arrival corridor, was previously in the reference scheme, the pink tunnel underground. At this stage, you're probably asking yourself, why are the facades inclined? Well, the answer in terms of the land side is easy. It's simply we're respecting the rights of lights of the existing neighbours on the land side. In terms of the air side, we're maximising the volume. And the other thing that the winning design did was it incorporated the vertical circulation stairs and escalators, separating the two passenger flows internally. So we don't have the boxes sticking out into the facade, thus minimizing the amount of envelope and minimizing carbon. So this also shows the reason for the inclined facade on the air side, which is that we had to respect a minimum offset to the nose cone of the nearest aircraft. And because the service road, which is C, needs to sit below the building, we had very long spans of 20 meters. B is the area that the pushbacks operate in. So RSHP, essentially a rebranding of Roger Stark Carbon Partners, which previously was Richard Rogers Partnership. And there's a common thread to the aviation projects in that we've tried to systemize the facade design. This is Barajas Airport Terminal 4 in Madrid. Most of you recognize this as Heathrow Terminal 5, and there you can see again the vertical circulation, which is behind the facade line, separating arriving and departing passengers. And just to give another example, this is a terminal building that we built in Lyon, in which the vertical circulation is perpendicular to another inclined facade. So if we just return to Geneva again, essentially the pier is 520 meters long, 20 meters wide. The plan at the bottom of the page is showing the service road with technical cores on the land side. The middle plan is departures in blue, in which you're traveling through the pink area, through passport control, left to right. The top plan is arrivals. We are coming up the valve and traveling from right to left, again going through passport control. In reference to the architecture of Louis Kahn, the pier is a simple diagram of servant cores on the land side serving the extrusion of the pier itself. So the client opted for a traditional procurement route. So the facades were fully detailed by the design team before we went to tender. This is one of the tender drawings. So it was tendered in March 2016. There was no contractor design element in the tender. These drawings were prepared by Acora, our subconsultant based in Paris, in which we've got a unitized triple glade facade with fixed brise-soleil on the land side to protect against, obviously for solar control. And if we just show the plan details, again, showing the unitized gasket system, used the external steel columns, which are tubes essentially, or a box section, a steel fabricated steel box section for wind loading. So those of you that represent the facade supply chain probably a bit surprised that the client chosen a traditional procurement route when you've obviously got so much input to give in the detailed design of the facade. And right enough, Gartner, who was the selected subcontractor by HRS, the Swiss general contractor, naturally came back with their own proposal, which hadn't been anticipated. On the left is the tender, the unitized, and on the right is Gartner's proposal, essentially a stick system, a bespoke stick system. And one of the reasons given for changing to a stick system was just the improved U values that the profiles gave. And after an intense period of negotiation, the client agreed to proceed with the contractor's proposal. And we worked collaboratively with them to improve and refine. And essentially, you can see on the right that the refined final detail offered much slimmer profiles compared with the original tender proposal. One of the obstacles we had to overcome, or one of the technical challenges, was there's a longitudinal slope along the jetty of 1 in 300. The facade's 10 meters high, the panels are 2.5. Because of manufacturing limitations, the 10 meters was split into 2 panels, and Gartner proposed supporting the upper panel with minimal pegs so that the lower panel could be removed in the case of a breakage. We should say that the 20-meter structural grid also had many challenges, including the structural tolerances and differential movement, and these accumulated up to 100 mils. So Gartner proposed a series of rigid and soft joints to accommodate to accommodate the differential movement, and rigid to resist racking. A mock-up was built, and this was an excellent means of choosing between 2 glazing suppliers, 2 different products. And it also proved to be a very worthwhile exercise to take the client through the design development. Facades were extensively performance tested at Gartner's facilities in Gundelfingen in Bavaria. And the facade installation started in 2018. So this shows the landside facade with the rectangular wind posts, the fixed brise aren't in place yet, and the towers to the back are the service cores I described previously. Because of the limitations, because it was an airfield and there was a radar height restriction, the facade was installed just using cherry pickers and avoiding tower cranes, and it was using cherry pickers and mobile cranes. So each panel is, just under 3 tons. And one of the most difficult details in terms of waterproofing to execute was this structural transition from outside to in. This was a key detail in terms of the design intent, that you can read the legibility of the transition. Obviously, there's a certain amount of overcladding that was required, but it runs all the way to here. This was extensively thermal modeled to ensure there wasn't any cold bridging or dew point issues. I think we can say we're very pleased with the actual precision achieved. As we're all aware, the challenges of climate change need innovative solutions to complex problems. And a highly insulated envelope, in this case triple glazing, is only one part of a strategy to reduce or reverse the carbon associated with construction. So although it was conceived a decade ago, the jetty is designed to be energy positive in operation. That's to say, it's designed to generate more electricity than it uses. Part of that strategy uses 110 geothermal piles which run underneath the jetty, connected to thermal ceilings. These can both cool and heat the building. And in the services gallery running under the jetty, there's another resource that will further help the energy balance. These are supply and return pipes which take water from Lake Geneva. The Genelac project is being rolled out over various parts of Geneva, and it can save up to 80% of the CO2 associated with cooling buildings. Rather like the geothermal piles, the system uses the thermal stability of the water in Lake Geneva. And by 2050, the Genelac system is projected to save 80,000 tons of CO2 per year for the city. Yeah, if we're serious about tackling the challenges of climate change, it's this level of infrastructure, infrastructure investment that will be required. So just moving on to the last part of my presentation. The pier was handed over in July 2021 and was operational by December 2021. This is a photo taken of the land side showing the fixed brise soleil and the triple glazed facade. This is the airside facade, where the brise soleil weren't required. And just to reiterate some earlier comments, the passenger experience has been optimized for both departing and arriving passenger flows, without one being prioritized over the other. You see, the arrivals corridor runs along the that's the arrivals corridor there, running along the airside facade, and those are the clear views of Geneva to the clear views to the Jura Mountains to the north. So the daylight and the views offered help to relieve some of the stress associated with air travel. It's been proven that relaxed passengers actually spend more time and more money in airport retail, and we tried to ensure that the passive wayfinding for the jetty was prioritized, with passengers able to find their departure gates without relying on signage. That brings an end to my presentation. Thank you for attending.
Well, thank you very much, Douglas, and thank you for a fascinating insight into the project. If I can ask you one question, was there a problem with, outward-facing glass onto air facilities has to be radar invisible? Was there any influence on the design from the radar point of view?
No, there are advantages in terms of glare that the inclined facade was 26 degrees to the vertical, but actually there weren't any issues raised in that respect. It was more a height restriction for radar. Yeah. So it was well received by those operating the airfield, the proposal.
Okay. Well, very good, thank you. Well, thank you very much indeed. Please thank Douglas for it. A wonderful talk this afternoon. And so we're moving on to our second speaker this afternoon. Our second speaker is Massimo Chies, who is a Director of Cost Management for Facades at AECOM. And Massimo will be speaking about the facade budget at early project stages. So Massimo, over to you. There he is.
Patrick.
Over to you.
Thank you. Thank you, Patrick. Yeah, as some of you know, I started my career as estimator for a large cladding contractor in Italy. This was in 2005. After a few weeks of training, I was shown the estimating tool of the company, and it was a very complicated tool. I had to prepare my first budget for a facade. And I was struggling. So I turned to my tender manager and I asked for some help. And he said, "Don't worry, Massimo, we'll do this together." And then he added something else. He said, "By the way, we've been told that the facade budget is £650 per square meter." And I started wondering, why 650? Why not 600 or 700? And who decided that rate? Okay, and how did they get to that number? Later on, in 2014, AECOM asked me to join their QS team in London, so I jumped to the other side of the fence, and I could find the answers to my queries, and I would like to share those with you today. So today, we will see the tools we use to establish the budget of our facades. We will see some of the key cost drivers for the facade. And in the end, I will touch very briefly about 3 challenges for our market. So this is the RIBA plan of work. It shows the various stages of a project from stage 0 to stage 7, so from conception to final use. And I would like to talk through the first few stages when we establish the budget, so from stage 0 to stage 4. So we know that there are many stakeholders involved in the design and delivery of a facade. So from the client, of course, the architect, all the consultants, and of course the contractors and the supply chain. The key thing here is that not all the stakeholders are involved in every stage of the project. At stage 0, simplifying a bit, the client takes a decision that he needs a new building. He appoints the architect, he appoints sometimes the project manager and the QS, and there is no design developed at stage 0. At stage 1, we run feasibility studies, and we need to answer this kind of queries. So, is the project big enough? How tall can we go? What is the budget? We get briefed by the client, and we are asked, cost consultants, to imagine an efficient solution for the facade. So we go back to our office, and we start picturing in our mind how the facade can be, and most of the times we think about something like this, very simple, repetitive. Then we meet the architect, and we need to get his ideas. And sometimes, not all the times, but sometimes he might start describing this facade. So, yeah. We have a problem, so we need to align the 2 ideas. Also because all the times clients prefer the facade on the right for the budget of the left. So what can we do? We use the first tool we have in our pockets, benchmarks. We see what other projects have done to deal with this problem. And AECOM have been involved in hundreds of projects in London and the rest of the UK, so we have all sorts of information on all those projects, the location, the typology of the building, the key stakeholders, areas, sizes, rates, design, everything, okay? So, very easy. We just filter the tool. This is just a screenshot of, the tool is much bigger, yeah, there are many more columns. We just filter a few columns until the architect is happy, so easy. No, it's not easy, because unfortunately, for the cost consultant, facade is a very bespoke package, probably the most bespoke in a building. But let's say that we are lucky, and we find in our past portfolio something that makes the architect happy. We still have some variables to consider. The first is inflation. We've seen the last few years what's happened to materials and labor costs. Then we have currency fluctuations. Most of the cladding contractors operating in the UK, they are actually based outside the UK, so we need to deal with euro versus pound exchange rate. And then we have updates to the building regulations. We know that Part L gets updated every once in a while, and it's very difficult to take track of this in the benchmarks. And then market conditions in general. We know the state of the economy is a key factor in the rate of our facade. Just to give you some reference, to build a medium-rise office building in London. Nowadays, it costs about £430 per square foot. And the average rate coming out from the benchmark tool for the facade is about £1,700 per square meter. So at the end of stage one, we make an informed decision. There are some, we discuss with the architect and the client, and we commit to a rate, and we kick off to stage two. Stage two is a very volatile stage. There are many more stakeholders involved, facade consultants, sustainability engineers, and I also start bothering many of the people in the room, to update my cost, my rates, and I try to be the link between the client team and the market, the facade industry. So what do I do? First of all, I do my own cost estimate. Thanks to my previous experience in contractors, I developed my own estimating tools, and to put together the cost of the materials, I made one specifically for glass, and then I make my assumptions for fabrication, transport, installation, design, management, the other preliminaries, cost, and of course overhead and profit. In parallel, I talk with the client team and the architects, and I agree a list of potential contractors that could deliver the facade. So, and I run a market testing with the design information I use to develop my own cost assessment. At the end of the market testing, we recap all the numbers, and we issue the cost plan to the client again. It's important to say that we don't have all the information that we will receive in later stages, so we need to make some allowance for contingencies. Stage 3 and Stage 4, things vary a lot with the procurement strategy that we decide with the client. Sometimes we can decide to negotiate the facade package with the contractor. Most of the times we run a competitive tender. And ideally we would like to involve cladding contractors as early as possible through a pre-construction services agreement, so that they can help the client team to develop the design and ask cost consultants to provide a more cost certainty to the budget. It's important also that during the PCSA we maintain control of the design before awarding the whole contract value. So we've seen how we get to the facade rate, what is actually driving the cost of our facade. Many things. One key factor is the wall-to-floor ratio. The wall-to-floor ratio measures the efficiency of the building layout. So we want to minimize the facade area and maximize the internal floor space of our buildings. Of course, we want the wall-to-floor ratio to be as low as possible. The wall-to-floor ratio depends on the shape of our floor plate. Ideally, from a wall-to-floor ratio perspective, a circular shape is the most efficient, but of course, it gets more difficult to partition and more expensive to partition a circular space. Squares are more efficient than rectangles, and as soon as we start introducing further corners in our floor plate, the efficiency keeps dropping. Then if we have two floor plates with the same shape and the same story high, the one with the longer perimeter, we have a higher efficiency. The problem with that is that we will have less light far from the facade. Story high, if we have a tall enough building and we manage to squeeze in an extra story by reducing the story high, we gain floor space area for the same facade area. And of course, facade depth. On the right, I have a naturally ventilated double skin with a very deep cavity for maintenance. And on the left, we have a more efficient closed cavity facade. Another cost driver, of course, is materials. They normally account for about 40% of the total value of a facade. I've seen on a couple of projects recently very deep reveals that didn't provide a meaningful shading for the windows. So any reduction in depth of the reveals can generate massive savings. Design complexity, of course, tall and repetitive buildings like the ones on the left are much cheaper than buildings with complex geometries and many different wall types. Also, design is linked to other cost factors like transport and installation. Panel size, there's always the big debate. Is there actually a universal optimal size? We usually say that 1,500 by story high is a good compromise between production, installation cost, and transport as well. We could go wider. We would save money for brackets. We would have less production cost and installation, but we need to make sure that we can vertically distribute and install the panels without the use of the tower crane. Of course, shaped panels are much more expensive than rectangular ones due to the extra cost of materials, assembly and machining. And another cost driver is joints, and I refer particularly to horizontal joints. This is the base study of a unitized facade. In blue, we have the glazed elements, and in red, the solid ones. Normally, for drainage reasons, the horizontal stack joint is continuous between the panels because we need to install the saddle gasket over the top transom. For architectural reasons, we might want to misalign the stack joint. That can be done, but it comes at a cost, of course, because we might need to install separately the solid panels over the backing unitized panels. Inflation, of course, on the top we have the cost of the raw aluminum for the last few years, and at the bottom we have the Dutch TTF. We've seen the massive impact that the pandemic had on the materials cost and the impact of the war in Ukraine to the energy costs. Other market conditions are the ones that we've seen when we were talking about benchmarks before, so currency fluctuations, import policies, updates to the building regs, and the state of the economy in general. So to conclude the presentation, I would like to talk very quickly about three challenges we have in front of us. The first one is, of course, net zero carbon. We should be familiar by now with the terms of embodied carbon and operational carbon. Up until a few years ago, all the focus was on reducing the operational carbon and reducing the U values of our envelopes. In the last few years, there's been a clear change in the focus, and we need to deal also with the embodied carbon. And this is important for the cladding contractors in the room. Please be aware that clients and design teams, they make choices over the cladding solutions at the very early stages of projects. So you need to be creative and try to improve your systems. Reliability of carbon assessments. Nowadays, embodied carbon calculation is a key deliverable on every tender. And it could be a criteria of choice at tender stage, so it needs to be a reliable assessment. Low carbon materials, we need to make sure that all our projects in the future can make use of recycled materials or low carbon materials, because at the moment they carry an important premium over standard materials. So with a widespread use, it will be better for the environment, of course. It will increase the demand, and it will hopefully reduce the rates. The second challenge is the Building Safety Act. It's a very complex topic, and it would require a separate presentation. But very briefly, just be aware that we will need to be competent and provide proof of competence to work on all our projects, not only the residential ones. And then the Building Safety Act will have also a massive impact on the procurement and the delivery of higher risk buildings. Inflation, again, we've already seen the impact of the war in the Middle East on the energy cost. Materials, they seem to have reduced in cost in the last few months, but unfortunately, labor rates, they keep rising. So just to recap, we've seen a few of the budget tools we use to establish the facade rate, and we've seen some of the key cost drivers for the facade. We cannot control some of these factors, inflation and market conditions, but we can control the other ones. So it's important that all the stakeholders agree a direction for the design at the early stages of the projects, and to make our buildings nice, but also profitable for clients and contractors. Thank you.
Well, thank you very much, Massimo. That's been a fascinating talk. And I have just one question for you.
Yep.
It's an easy one. I can understand if you're creating a database of cost, you've got many projects within AECOM that you can draw from for information. But is there any sharing of information between cost consultants? Do you have any? Are you sharing it amongst yourselves within the industry? Is there a wider sharing?
Well, let's say that when I produce my cost assessments, I try to cover as many facade types as possible on the projects. But sometimes I have to rely on benchmarks. And of course, I talk all the time with many of the people in the room, with cladding contractors, suppliers. It's probably my main task in AECOM to keep this discussion open.
Okay, so you're gathering information from suppliers and from
contractors and suppliers as well. Yes.
Very good. Well, thank you very much. Thank you again, Massimo.
Thank you.
Please give a round of applause. So next we have up a talk from two speakers. We have Ana Araújo, who is a partner at Bureau Happold, and Patrick Campbell, who's a senior partner at Foster & Partners. And they are going to be speaking to us about the Whiteley's renovation in Queensway. Welcome to the stage.
Thank you very much.
So please give a warm round of applause for Anna and Patrick. Thank you.
From the beginning. Yeah, thank you. Thank you very much. And it's great to be hosted here, so thank you very much for inviting both of us. It's lovely to be here. It's lovely to see so many familiar faces at the event. We are super pleased to be talking about a project that is still live, still going. It's been going for about 10 years, so it's a bit of a labor of love for us and I'm sure for a few others in the event. Today's really to talk about the facade, the heritage fabric, but also how that has had an amazing impact and inspiration on the overall project. We're talking about conservation, adaptation, and the upgrade of the existing facades, which has been a huge technical challenge as well as an architectural challenge, and that's really what we wanted to get into today. A little bit first about the project. Not everyone knows where it is. It is in Queensway, which is a principal road just to the east of Notting Hill, just to the west of Paddington. It's an extraordinary little road that has been kind of lost in plain sight for so many years. It's a 5-minute walk from Paddington. It's a 5-minute walk from a royal palace, but it's kind of lost its mojo, and that's what we're trying to sort of bring back. It was the brainchild of this fantastic man called William Whiteley, who was a northern merchant who came down to London and thought that he would compete with the Selfridges, the Harrods, and all the rest of it. So the story goes that he had £10 in his pocket and he went to this place. He, through a series of mysterious insurance claims on even more mysterious fires, he slowly built up his empire. to the extent where he then commissioned Beltran Joas, the sort of fine architects of the day, to produce something that was completely out of scale with the neighboring kind of stucco-fronted Notting Hill squares. And here he wanted to create something that was unthought of in the day, which was retailer's experience. He wanted to create the world's biggest shop. Wow. And he came up with these very flamboyant, very lavish facades, including terraces to take the air. There were places to buy pins and elephants. There were places to see fashion shows. There were all sorts of things. It was a very, very, very elaborate kind of piece of theatre. It's a Grade 2 listed building. It was when we started. It will be when we finish, we hope. And it's made up of some wonderful bits of history, bits of material, some fantastic pieces of sculpture, beautifully made existing windows, existing stonework, a very sort of highly detailed facade that in principle is 4 stories high, 180 meters long in the north-south direction. On the ground and first floor is a Welsh granite, and above that is Portland stone. There are elements of greater ornamentation in the southern cupola and the central clock tower, which we'll talk about. And then there are other elements of really interesting heritage facade. There's a central screen, which we've played around with and relocated to make sure that it's absolutely at the heart of the project moving forward. Also an existing dome, a beautiful thing, and an existing staircase. So a number of kind of key assets that we've put front and center in the project moving forward. It very much lost its soul, its spirit from the high days of William Whiteley. In the 1950s, it started to kind of recede on itself, and the upper floors were converted to office space in a really kind of not particularly sympathetic way. Lots and lots of redevelopment saw the facade being retained in front of some, again, unsympathetic developments to create a very large car park in the middle of London. That's not what cities are all about, what they shouldn't be about. And you can see how it became a very internal and rather dreary place. And it closed before the pandemic, but it certainly wouldn't have survived if it had carried on anyway. So what was the ambition? We had a fantastic, far-sighted client who wanted to see this as the rebirth of Queensway. As I say, it was one of the kind of the last of the park-facing neighborhoods to really kind of fulfill its full potential. So what we wanted to do was to make the facade and the heritage story at the very, very center of the redevelopment. So the idea of 180-meter long to completely refurbish and restore the facade in a super sensitive way, but obviously lifting the technical performance of all of those elements to the max, thinking about combustibility, thinking about how the supply chain would feed into that. But just to give you a sense of scale, so we've got 180 meters, we've got the 4-story high, and I'm going to try and point to this. Here we go. So 4 stories high, 180 meters in length, an existing cupola to the south, which was then matched with a new, because it was never installed in the first place, at the north, the central dome, and then 3 stories of additional accommodation that was added on top of the heritage facade. When we first started the project, the inside of the building was, as I say, very, very dull, very unloved, to the extent where there was an A board on the pavement saying shopping centre. You know, no one knew that it was there. So what we wanted to do was to think about how we could really cleverly adapt the existing fabric. So we took the central screen, which you can see behind the big W, which we have got rid of finally. That big screen was moved to the northern end of the site and then became the entrance to the new Six Senses Hotel, which is about 110-room sustainable wellness hotel. So that gave a much better sort of setting to the entrance to that hotel, but allowed us to open up the heart of the building to a new pedestrian and public space at the center of the plan. And then this is the new entrance to the hotel. You can see it was once the entrance to the car park, where all sorts of antisocial things went on, and what we wanted to do was to breathe life into that rear street as well. As I say, the facade this isn't a story about the facade and everything new behind. The facade is absolutely at the heart of every design decision we made because it informed the plan form, it informed the grain, the grid of the building, so each into column dimension is about 4.5 meters, which is roughly the width of a terrace house in London, just to give you a sense of scale. The windows are 4.5, 6 meters high. So that again told us that that's how the new building had to kind of follow suit. And so to create these wonderful lateral apartments, all with fantastic external space to the rear. And then taking on those wonderful idiosyncratic spaces on the corners or at the tops of the building as well. We wouldn't be here today if it wasn't obviously for the client making that call to buy the building in the first place, but also a huge range of experts in the design team and in the contracting team to really think about how we bring together the 1 million square feet, 100% BIM obviously, but every single room is different because of the way that it has to interface with that heritage facade. And I think that's been an absolute kind of tribute to the kind of attention to detail that we've seen from the entire project team.
Thank you. Thank you, Patrick. So Patrick explained a little bit about the building that was there in the beginning, a bit run down, protected, lots of merit to save as much of the heritage material as possible. So something that we had to define quite in the beginning was what's the strategy for surveys, what unknowns we have at the moment to be able to develop the design and start making the decisions of what this project should be, that we need to start tackling now, and then dividing those surveys almost into stages. What can we do pre-contract to enable the design decisions? What needs to come next? We had this amazing ambition from the client and the architect on what could be achieved of this building, and that's made us have to do very early days a number of surveys that most projects don't have. So just to guide you a little bit through it, I think the first step was a very thorough archive research that Foster's did, we did. Everyone really digged into all sources possible that we could find. And this project was actually quite good in obtaining very relevant information early on. You can see here, for example, let me see if I can point as well. We were able to find a photograph of the day of the opening of the shopping center. So in terms of getting relevant information of what was the original intent, you can immediately see how this is quite valuable. Something that came to our attention immediately was that potentially the white windows that we had seen when we got to site were not the original color. So you start to build the hints of what's there. Also, very good information about the retention that had already happened in the 80s, that from a structural perspective gave us very good information about that facade and probably helping us to focus where we should start opening up and investigating. But also things just as great as this detail from 1908, showing where the embedded steel in the facade was. Not all projects have the benefit of having that, but again, it saved a lot of time and investment in intrusive investigations trying to collate this information. So the archive research in the very beginning was actually very powerful. Obviously, and particularly considering that this was a listed building, but just for its relevance, having informal planning conversations that Foster's led, just really trying to get a sense of what are the elements that really matter, that are really important, that we really need to help protect. It really helps to also guide those design decisions. As part of those conversations, one element that came out was the absolute love that not only us, but the planners as well had for the heritage windows that were there. The perspective always from a distance of who looks at the building is, it looks about right. And normally 90% of the times when you start to look closer, probably it's not in such a good condition as we expected, or maybe not so much of the original material is there as we expected. So what we discussed with the client, and kudos to the client that was very brave in investing at stage 3 of the design in a very detailed condition survey that measured, mapped, cataloged all of those windows to help inform those planning conversations and help us understand how much of that original material was there, what type of materials are there, even if we want to replicate. So again, very valuable information. Then obviously the masonry elements of the building, and we're talking not just about mapping up the defects, and this brought very early engagement of contractors that helped with the surveys, Bay in this case, to really help map up all the defects, photograph, because these surveys are always a point in time, and bearing in mind that there was going to be a retention scheme coming along where there was vibration movement happening to that facade, it was very important to catalog what was there before and monitor any alterations. And then obviously start intrusive investigations. We had those clues in the beginning of what might be there in that facade, but we could then open up in limited locations. The building was still in operation. There was only so much we can do, so we had to be very targeted on the information we were trying to obtain in those early days. But we were able to get a lot of information, not just about condition, location, but start doing some structural assessments of that facade as well. I could go on the list of surveys that were mapped out from the beginning, some that then continued when the contractors were on board. But in these types of projects, we really do need to think laterally. Just thinking, for example, the color of the windows and doing paint analysis through all the layers to try to match what's the role that currently would be best connected with what was the original color of the windows. Just the presence of lead content in the paint that would shift the decisions in terms of doing repairs on site, doing repairs off site. This is all very valuable information that as early as we can have on a project, and in this project we were very lucky to be able to do those early days, really help progress in the right direction. We had to select a few stories. This project could have probably 1,000 stories to tell. It's a huge in scale. We chose Central Dome as one of the stories to tell because probably I'll let Patrick tell a little bit about the intent for it.
Well, if I just jump in for a second, what I think, as Anna was just saying, is that at the heart of this is a fantastic collaboration across the project team, but also with the different stakeholders. In this case with Westminster, but also with the local neighborhood societies, because it's trying to identify what are the most important parts of the heritage story and how faithfully should we look to repurpose them. Obviously, understanding that there are new criteria that we have to kind of work to in terms of health and safety, in terms of combustibility, in terms of thermal performance. And so it's allowed us to kind of be very innovative in terms of how we approach this. In partnership with all of those different players. The Central Dome itself is a beautiful thing. It's a twin-skinned piece. The inner skin was historically polycarbonate, which obviously, for all sorts of fire safety issues, couldn't be retained. But then trying to understand the load-bearing capacity of how we might introduce a new internal skin of glass. So we've been thinking long and hard about how that might be reworked and trying to understand which of the elements of the existing structure we could reuse. And so that's led to a number of different approaches. But at the heart of it is that this needed to remain the focal point of the project. And I think that was the key kind of goal of everyone in the project.
And being lifted to a new position, even in level, new structure supporting it. So just guiding through it, when we started looking at it, we tried to identify what were the main components and how much can we salvage, bearing in mind that this dome would have to be dismantled, taken off site, waiting for the new structure to come in and then be reinstalled. We followed a lot of those processes of surveys that I talked about, but the main elements that we looked at were the main structural steel, the ribs and the purlins, the aluminum framing that was supporting the glazing, and the glass or polycarbonate in the inner dome, and starting to draw what the system was to get records of it. There was a lot done from testing for material identification, measured surveys conducted by the contractor, condition analysis of the components, stress tests and metallurgical analysis to understand the capacity from a structural perspective, and then doing those in-house structural calculations and assessments to see if with the new loads of the project and the new conditions, these materials could be reused. So the outcome of this exercise was that the main structural steel, the ribs and the purlins, could be repaired and reused after being taken off-site, and they had to be very carefully dismantled, catalogued, and so on. The aluminium framing, though, it was in very poor condition, and it had insufficient load-bearing capacity, so we couldn't reuse in the new project. And the glass as well, the external glass, the wired glass that was there, single panes, not just was in poor condition and insufficient load capacity, but also from a safety perspective, we wanted to provide something more robust for the new project. So the next step was to help with the selection of a new off-the-shelf patent glazing system that could provide this extra performance that we were looking after. You can see here on the right a photograph of the new system that is now being installed almost complete on site, and just a view of what that dome looks on site, still works in progress, but you can see there in white the structural elements that were able to be reused, and all the rest just replicated and mimicking the original as faithfully as possible. Another story that I would like to tell, because it was so central in all the conversations throughout the years, was the story about the heritage windows. It's part of the identity of the building when you go through Queensway. As I said, when you start looking closely, things don't look as well as they do from the distance. And we did that very detailed condition survey to help inform how much could be kept or not, what materials were there, what sight lines we should be able to respect. But this was the condition. And actually, throughout the years, a lot of the original handles, spannulets, everything had been removed. So there was very little left of those windows. So the exercise we went through is saying what can be salvaged and how much can be repaired and how would it look like if it was repaired. And again, we were very lucky to have a client that followed our advice and from early days invested in real scale mock-ups. And again, Patrick gave an indication of the dimension of these windows, 4 meters, 5 meters tall. And it was really putting side by side these options of repairing, putting secondary glazing to give the performance, or finding a solution that could respect the sight lines, could look like the original, and integrate as much of the heritage fabric as possible. You can see here various VMUs that were done through the years, so there was a lot of visits to specialists in repairs of steel windows to see what could be achieved, because we had to make this realistic assessment, what can be achieved by the supply chain. And you can see here what was the final VMU that was assessed by Historic England and Westminster, and with lots of praise, because it really not just meets the sight lines of the original, is a thermally broken steel system with double glazing, but it incorporates the heritage mullions, so this is heritage material that was incorporated. In this image you don't see, but there's a lot of the pieces of the balconies above that were also reused. You'll see in the next photograph. We tried to use as many of the glazing bars that went into the frame, so there's a lot of the original fabric still in those windows. So this is how it looks like today. Going back to that darker color, that was the original intent, and going back to what was the 1908 intention for the building. So a lot of existing fabric, even though it's a system that performs as per current requirements. You can see here a lot of the cast iron, the balconies, the mullions that are part of the 1908 fabric of the building. Final story is just the deconstruction of site storage and reinstatement of the masonry facade features, and that we talk about the the entrance screen that Patrick referenced to, the south cupola, the clock tower, the dome, which we knew because of the retention scheme would have to be taken off-site, being dismantled very carefully, and then reinstalled with new detailing and meeting a different type of performance to incorporate in residential and hotel use. So again, early contact with the supply chain to understand what they would need to make this happen was crucial. And I chose some of these photographs because you can see here the very special mason scaffolds that you need to be able to even dismantle some of these features, bearing in mind that there was a retention scheme coming. Being able to advise and understand that actually the retention scheme needs to wait for these scaffolds to go up and down, it has a real impact in terms of program and budget, and really enabling for that is quite important. So there was a lot of detailed survey during the dismantling. Once the scaffold was there, you can see there just a little bit of the work that Pei did in mapping out the different pieces of stone as they were removing layer by layer, using it as a map so that they could rebuild after. Some images of when they were dismantling the central dome as well, the clock tower. The elements being protected and catalogued on site and then taken off-site for storage. They were off-site for years. So even visiting those storage units every now and then just to make sure and give reassurances that all of that material was in good condition. And then the reconstruction, giving new structural elements to support these features, and just rebuilding using all of that information that was catalogued through the years to bring these elements back to life and incorporate them in the new building. I'll pass to you, Patrick, if you want to close off.
I think one last slide. So just to say, we are super close to completion early next year. It's been an absolutely fantastic journey that I've been part of, that we've been part of, that also gives us a great access and a celebration of sort of some of the amazing trade contractors that the industry has in terms of fettlers looking at the bespoke steel windows, or the stonemasons looking at the individual fingers of some of these statues. It's an absolute joy to be part of that process. So, any questions at all?
Thank you.
Thank you very much.
Thank you. Thank you, Anna and Patrick. What a wonderful and fascinating presentation. I had just one question for you. The double dome, do you have any idea why it was constructed originally as a double dome? Do you have any thoughts on how that came to be? It's very unusual.
It's a very good question. When we first started, we asked ourselves many times, why did they build that part of the building like that? And sometimes we had answers, and sometimes it was pure speculation. So in terms of the dome, I think there was the piece about trying to access and how that might work. In the original piece, there wasn't an external gantry, there was just an interstitial gantry.
Yes.
So perhaps that was part of the story.
Yeah. Okay, well, it's a fascinating talk. Well, thank you so much. And it's wonderful to see such a fine building restored. And the amount of work that's gone into it is truly amazing. So thank you very much for a wonderful presentation. Please
thank you very much.
Thank our speakers. Well done. Thank you. Thank you. And so up next we have a talk from Rudolf Zelmer, who's coming up onto the stage now. Rudolf is an architect with iRise, and he will be speaking about dynamic liquid crystal glazing to enhance building performance. So Rudolf is making his way up, and he's got some samples as well down here. Rudolf, I'm presuming that we can hand these round, can we?
Yeah.
Okay.
We should have.
All right, Rudolf Zelmer, please welcome Rudolf.
So the presenter is here? Yeah. Yes, hello. My name is Rudolf Zelmer. I'm an architect at iRise Merck, responsible for architecture projects with iRise with switchable glazing. So, what we are building for? As architects, we are mostly building for people, we're building for environment, we're building for human being. So, daylight is one of the essential things we want to have in our building. Always, we want to have daylight. Why? When you're going somewhere in a restaurant, where is your seating place you preferred always? It's always near the window. You want to have this daylight. Daylight is beautiful. Daylight gives us some kind of wellness inside, and we love this. Exception, we don't like glare. We don't like too much sun, and we don't like that our building are some kind of overheated. So the heat is a problem, sun glare is a problem. And we mostly don't want to like some kind of shading system that have to be repaired all the years, have to be exchanged, are dirty, are ugly for the architecture on the building. And this is what we can find a solution for with liquid crystal. So liquid crystal is an integrated solar shading solution for facades. With the technology from the company Merck. Merck iRise is in this case the same. So what is behind who we are? We are Merck, the leading company for liquid crystal technology. And it was founded 1904, so a few years ago. And it was founded, and we are mostly a supplier for Samsung for around 65% of all liquid crystals in display. And this display technology to have a new kind of dynamic windows, we translated into architecture. And now we have architecture facades with liquid crystal technology on the market since a few years. How does it work? The best explanation is if you see the liquid crystals switching there, the liquid crystals have some molecules in some black molecules with them, and they are switching from some kind of open space to closed space. The liquid crystals, they are absolutely transparent, and the molecules are absolutely black, so very high color trueness, and they can switch dimmable with 256 stages. You don't need all them, but it's dimmable, and you can exactly go with the sun. When there's some small cloudy, it's dimming a little bit, a few percent down or up and down. You can exactly do this in the glass in between two glasses. So on the left, on the right-hand side, here, the pointer, yeah, maybe the other one. So here you see the electronic coating. On the other hand, the electronic coating as well. And you can imagine it's like a compass. The liquid crystals are switching from closed to open in a dimmable state. And these liquid crystals, in between these two glasses, this is only around 30% of 1 millimeter. This is the way the liquid crystals are working in two stages. So the next, you can see our standard double glass unit. Mostly it's around in Switzerland we are working with triple glass units, in other areas with double glass units. Outside you have always a cover sheet, a cover glass. It depends on the project. On some projects we need 5, 6, 4 or 10, even 12 millimeters for a cover sheet. Then you have the iRise cell. 2 cells with 2 times 4 millimeter glass in between the liquid crystals. So the sun shading systems has to be outside. It's exactly like this here. And then you have a PVB layer for sure. You have the secondary seal, primary seal, spacer, coating, inner pane, middle pane, or the inner pane in a triple glass unit. So this is the technology behind. Yeah. What is right now a classical solution for sun shading? The classical solution for sun shading are mechanical shading outside. You always have this shading for sure. It works. You have maintenance, mostly high maintenance when it's a high-rising building, for example, or a very complicated form, and you cannot really enter every stage to maintain this. You block the view. People are inside, sitting in the summer. So we have made this investigation and saw that in summer, for example, people in 30% of the day sitting behind closed blinds. So it blocks the daylight, and it's slow and noisy. So on the next slide, you see what is the advantage on iRise on the picture below. The same like shading, but there's no maintenance, absolutely no maintenance. It keeps the view. In a sunny day, you can look outside. Nothing is blocking the view. You have some kind of daylight autonomy, fast and silent, and no peak loads. And you look on the cost. You don't have to look always on the invest only. When you only look on the invest, for sure, it's an expensive solution. But when you're looking on the whole time, for example, 25 or 40 years, it absolutely makes sense. When you don't have maintenance, the most costs not only are in investment, a lot of costs are during maintenance the building, clean the building, or replace the sun shading system. That's pretty expensive. So after around between 8 and 10 years, it's much more cheaper to invest a little bit more in a technical dynamic glazing, and it works without noise, without anything. So this is an example on a project we've made in Switzerland, in Vevey, near Geneva, so Geneva again. It's a project with more than nearly 2,000 square meter glass, and for sure, when I'm sitting there, I want to see the mountains all the day, in summer and in winter. And this is what a solution gives you, really a high appreciated sitting there, looking on the mountains, working a little bit, but see the mountains. Yeah, all the time, and not in 30% don't see nothing. I will just go to the slides. Sustainable solution. For sure, when you look on the overall costs on a building, on the overall costs on investment for a building, it's a sustainable solution because building operation is 27%, building construction and so on. So I mentioned this before. When you compare our system, iRise, with other glass solutions, you see a double glass has a carbon comparison of around 100 kilogram CO2. Then you have this external blind, and both together you have around 450 kilogram CO2 per square meter. When you look on our solution, even on a double glass solution, here, with our glass, with iRise, you have the sun shading inside, you're around 220 kilogram per kilogram CO2 per square meter equivalent. And a triple glass unit on this row is, so it's approx 50% lower than normal glass in and classical external shading. Sustainable solution, I will not go to each topic, but you know exactly social, economy, environment. I will also only point out this important topic. Social improves thermal comfort up to 10%. The tenant can have to pay, or the investment can get more money for the rental fees. It improves health and productivity up to 5 years. We have made this solution for a lot of projects and calculated it exactly. iRise life cycle. So after production, manufacturing, you see the glass can be absolutely recycled, like similar safety glass. There's nothing else. And you can go with this glass and recycle this again. Yeah, this was the project we have made an opening 2 weeks ago in Switzerland. This is the Google headquarters in Switzerland, in Zurich. And from Swiss Prime, Urs Baumann, there was a testimony on this. I will not go to each topic, but they were pretty happy to have this glass on site. They don't need anything else than dynamic glass. So SNBC, this is the equivalent like LEED, or in Germany we have DG and B. They had very positive impact on this certification because of our glass and the healthy and well-being inside staying there, and the material resources. You don't need sun shading, you only need this one glass. Yeah, on this topic, 30%, I mentioned already. This means, on this project SMZ, in Müllerstraße, there was a building from the 80s, and the architects really made a lot of effort to recycle every aluminium things, recycle as much as possible to have a low carbon footprint as much as possible, and there our glass was very helpful for them. The situation before, and for sure here after, really a solution like you wish. Calculating case study, we have made a calculation what kind of mixture in darkness they need, and we help the customer with this as well. So this is the building from outside. Inside, there was about 3,300 square meter glass, more than 1,000 panels of liquid crystal dynamic glass. And yeah, not only on the facade, we have made a project in Zurich as well for a roof. So to summarize, you have always color neutrality in comparison to other technologies. You have always access to daylight and thermal comfort, and is fast switching and instantly in response like the sun is going. You don't need to be worried that there is cloudy, not cloudy sky. The dynamic glass is exactly going the same way like the cloudy and sunny sky. Yeah, these are the projects, realized projects, some of them summarized here. And what's important right now, and we count this on each big project as well, how many tons CO2 you can save in comparison to your regular glazing you would have. Because you don't have this two kind of sun shading and glass all in one glass. For example, on this SMZ project here, we saved 750 tons CO2 was saved only by choosing the, I would say, the right glass, but the dynamic glass with liquid crystal technology. Yeah, this is a small video from the installation on SMZ. This is the glass package. It was about 68 millimeters with the cover glass, with all the liquid crystal and glass panes inside, a triple glass unit. They were prefabricated in the company Epley, for example, in this construction site. And now the building is ready. Tender is by Google. And you see the glass is not, you don't have any other things beside. You only have this pure architecture with glass and sun shading in one or in few millimeters. Instead of, for example, closed cavity, you need 700, 800, it depends on the system, millimeters. With our glass, you only need 68 millimeters. So it's really a difference in between for a place you can use in another way, not only for facade or whatever. Yes, it's a nice area, and then this, for sure, you need a view you don't want to have in this project or in other projects, really looking on external blinds. Yeah, so I will invite you to see the glass in live. It switches from dark to bright, and it's really dimmable on each stage you need And exactly this is what the clouds and the sun is doing when it's going down and bright and sunny again. It's exactly like we can do with dynamic glazing. Just try out, and yeah, thank you for your attention.
Well, thank you very much, Rudolf. Thank you for your fascinating talk on liquid crystal. It's an amazing technology, and I know from previous discussions that it can go down to, so the minimum light transmission is going to be about 4%.
Yeah.
If you have it in a double glazed unit, what is your maximum light transmission?
The maximum light transmission in a triple glass unit.
Yes, in a double glazed unit.
Yeah, in a triple glass, for example, you have a maximum light transmission of 45 in the bright state.
Okay.
In the mixture, that's pretty bright.
Yes.
Then we have a dark mixture. The darkest mixture is 34%.
Right.
Switching to 4% or even 3% in some projects we have
All
seen.
the way down to 4%.
Yeah.
So
it's dynamic, and the G value is dynamic as well.
Yes.
We architects have to think a new way of designing a building, because the G value is not a one fix again. The G value is, for example, switching in a triple glass unit between 23 and 7. Dynamic and without steps.
Okay, and it's obviously toughened glass because there's going to be a lot of energy absorbed by the glass itself.
Yeah.
Well, thank you very much indeed for a fascinating presentation.
Yeah.
Please give a round of applause to Rudolf as he leaves the stage. Thank you.
Thank you.
Okay, and so next we welcome Stephanie Godard, who is the Business Development Manager at Eastman, and Stephanie is going to be talking about a bird protection safety interlayer with SafeFlex FlySafe 3D. And please welcome Stephanie to the stage. Thank you.
Thank you. Well, thank you, Patrick, and good afternoon, ladies and gentlemen. Let me take you through a subject that we introduced the first time at Zak Manchester last year, and it has been evolving since then. So we'll have a brief introduction to what SafeFlex is and what it brings to the world of facade before going to the main subject, that is the bird-friendly glazing solution. We'll look at what it means in terms of building regulation, including sustainable standard, and also what it means to use SafeFlex FlySafe 3D in glass design before looking at the path forward. So what is SafeFlex? Well, SafeFlex is, for 85 years, the high-performance PVB interlayer that is being used between two panes of glass to keep shattered glass in place. It's been specified in many iconic buildings around the globe by facade engineer and architects for its safety and security feature, but also by glass processors and facade industry that can rely on our expertise and services. Over the last 20 years, continuous innovation has led to add acoustic comfort, solar control, extra UV cut, but also structural performance in order to reduce the glass thicknesses. With our colored interlayer, Vanciva, that we can stack between two panes of glass up to 4 layers, we offer more than 17,000 tints, allowing to sign very unique design feature. So now, what about birds and glass? If it works. Oops, sorry. Well, glass is undetectable by birds every time there is a reflection of trees, of landscape, or sky in a facade. It's a potential threat for birds. Every time there is open spaces with lights on or trees behind, this is a potential threat as well for birds. And unfortunately, the number of fatalities are quite impressive and participate in the loss of biodiversity. There are solutions, fortunately, but what should you expect from those solutions? Well, first of all, you should expect that they've been proven, that they've been tested. There is no norms on the market to test the effectiveness of those solutions, but there are scientific protocols by ornithologists to say whether a solution is effective or not. One should also expect, those solutions to have a minimal impact on the human vision, but also to respect the aesthetic of the overall building. And of course, no one in this room would ever specify glass without the best solar and thermal properties, would ever specify a solution that would need to be replaced every so often because it's not durable. And if we can avoid, extra treatment, heat treatment in particular, and thus saving CO2 emission, that is even better. So what are these bird-friendly solutions? We've all seen these bird silhouettes on glasses. You can see them on walls, along the highways. Well, clearly, unfortunately, those silhouettes are not durable. Not only they're not durable, but they're not effective. It's the ornithologists who say that. Then we have silkscreen, acid-etched, UV-treated glass, and they are highly effective solutions. Unfortunately, sometimes to the detriment of light transmission, because the glass coverage is quite high. When it comes to SafeFlex FlySafe 3D, well, like everything we're doing, it's an in-glass solution. It brings also safety and security, so it's a durable solution. And this is a real case scenario there, where you see the reflection of that tree. And this is actually the window of one of my colleagues. And he sees the fatalities of birds going down to zero. So these sequences that are present between the PVB are highly visible obstacles that the birds are safely avoiding. And it's been tested by the American Bird Conservancy and the WUA in Austria. There's only 2 places in the world where you can actually test those solutions. So what we've done, we've mapped all these solutions, and we've taken into account the percentage of approaches as tested by the ornithologist on the y-axis, and on the x-axis, we've put the pattern coverage. Well, you see where our SafeFlex FlySafe 3D is laying, so it's in the lower left quadrants, with less than 1% coverage of the glass and less than 10% of approaches considered by the ornithologist as being highly efficient. Well, this mapping is updated on a continuous basis because there's more and more solution being tested. With this slide, I would like to draw your attention, and I mentioned it before, to the fact that both transmission and reflection is important. The WUA in Austria is testing those solutions for both transmission and reflection. That is an important factor. This document here was published in December 2022, So it's a very recent document. There is an even more complete document by Vogelwarte, that's a Swiss organization, that is listed all these solutions and what to do and what not to do. So what, in terms of building regulations? Well, our chairman today in this session, when we introduced this subject at Zak Manchester, came to me, to our tabletop, and he said, I'm very interested in birds, personally. I don't know if you remember that, Patrick. And he said, but as a facade engineer, I never had any request for that. Well, fortunately, like sustainability, biodiversity, things are changing in the good direction very quickly. So, in terms of building regulation, in North America, there was already a number of legislation attached to cities most of the time. What we see is more and more of those legislation being adopted. On this side of the ocean, the state of Hesse has also adopted the Nature Conservation Act to prevent the bird to strike onto glass surfaces. When we went to ABS last week, we also learned that such a legislation would be adopted in 2025 in Finland. That is tomorrow, basically. In France, labels such as biodiversity will only be granted because if a bird glazing solution is adopted when needed. Just as a reminder, using Saflex FlySafe 3D is eligible to 1 lead point under the pilot credit SSPC 55. So now, what about glass design and Saflex FlySafe 3D? Well, I'd like to remind you that because of the low coverage of the glass surface by the sequence, there is no impact on the light transmission and on the solar factor. Also, the glass and the glass supplier can be chosen independently from the bird-friendly solution. That gives some freedom, of course. And moreover, and more important, we carried out a modeling study to map the configuration using the low E coating and the solar coating that would remain effective with the Saflex FlySafe 3D. Because of the testing is carried out by the WUA only in a certain period of the year, all the configurations that are available here to you, the facade engineer and architect cannot be tested. So we had to find boundaries, where low E coating and solar coating would be used, with Saflex FlySafe 3D without being tested. So we considered the properties, first of all with the low E coating for double glazing unit and triple glazing unit. For solar coating, we looked at the reflection and the transmission. And we sat with the ornithologist and we established these boundaries. So it also allows, if you have a configuration, to say ahead whether that will work, whether that will actually be effective. So it allows to have no compromise on the thermal and on the solar properties with this Saflex FlySafe 3D. The summary of the outcome is this wide range of conventional low E coating, solar coating that can be used. without having to be tested. With that in mind, the first SafeFlex FlySafe 3D that we launched last year was the 9mm sequence, shiny for the exterior, black on the interior, in order to minimize the disruption to the human vision. And we recently launched the matte silver for the exterior sequence and always black in the interior. We also have smaller sequence, 6mm in diameter, both in shiny and in silver matte, but also for applications such as anti-noise walls or rooftop that are very fashionable these days with a lot of vegetation. We have shiny and shiny on both sides. And we have them on our tabletop if you want to see them live in a laminated glass. I'm not going to go through all the details of this slide, but I would like to point out two things. First of all, like every other interlayer that we are offering, we can go up to 3.2 meter width, allowing, big pieces of glass to be installed, and the surface coverage, for the 6mm sequence is less than 0.5%, and for the 9mm sequence, it's less than 1%. So what about the path forward? So it seems quite clear that we will not go back. And actually, for Patrick's sake, there is a project in the UK at the moment. It's driven by building owners, more and more regulation being in place, and there are continued offer development with the PVB interlayer solutions. So, I would like to end this presentation by our very first project that has been installed in Germany, the Helios School in Cologne, with very high glasses, 5 meter high. And as a matter of fact, I started my presentation with a view from inside as well. So you could see both from the exterior and the interior. Thank you for your attention.
Thank you, Stephanie. Thank you. Fascinating. And what an amazing statistic that 1 billion birds die annually, 1 billion, from collision with glass. And really, in a world where we're losing species, where we're losing our natural world, literally as we speak, what an important product this could be in the reduction of bird deaths due to impact with glass.
Indeed.
So thank you very much for a fascinating presentation.
Very welcome.
And we look forward to seeing the Helios built. And let's all go and have a look at it, shall we?
Thank you.
Okay.
Thank you very much.
Thank you. Thank you, Stephanie. Please. So lastly, we have a panel discussion. And the discussion will be on 21 Moorfields, building on air. And I'm sure that the team are going to explain what that's all about. So they'll be looking at the design challenges and concept, structural solutions, glazing and envelope at this particular project, along with the construction strategy. Our moderator this afternoon for the panel discussion is Giles Martin, who is a director at Wilkinson Air. So, Giles, please come up and introduce your team. Thank you. Please give a round of applause for Giles and say thank you very much.
Well, I'll make a start. Shane will make his presence very well felt as he's 6'7" with size 15 shoes. You'll see him in a minute. Well, when Zak asked us to do this talk, they suggested doing it as a panel discussion. Although we're going to do it, there's actually 4 different perspectives of looking at the same challenge. And we're all members of the design team, and rather than introduce them now, I'll introduce them one at a time. And when we got together to discuss it, we agreed this is the most difficult bloody job we've ever done in our lives, and we've taken the theme of challenges to take you through the project. I'm Giles Martin. I'm a design director for Wilkinson-Eyre. I have led the project for 11 years. Wilkinson-Eyre do a lot of long-span structures, bridges, stations, arenas, and although this is ostensibly an office building, it is in fact a bridge over a station, so it's very suited to our core skills. Here's a view of the building from the northwest. It's in a ridge of tall buildings between two conservation areas, Finsbury Circus and the Barbican, and it's very constrained by how high and where it can build. The diagonal cut is a St. Paul's view, which you'll see later in a minute. Here's the same view just after the Second World War. The station, highlighted in blue, of course, was a cut-and-cover, just subsurface station with canopies, people coming down from Moorgate to the north. This is a view you might recognize if you ever used the station. And they built a oversight development integrally with building the station, which is quite unusual for the 60s. So the columns in the center of the platform and the structure of your head is in fact part of the oversight development. And here it is when we took it on. Well, actually Crossrail knocked a big chunk of it down, but it's a very unflexible building. You used to follow courtyards, a yellow line through courtyards to get to the Barbican to the west. And it's been empty, it stood empty for 15 years, really due to the fact that it wasn't working as it should. That all changed when Crossrail came along. Crossrail, Liverpool Street is also by Wilkinson-Eyre. The trains are so long that the Moorgate station, the Moorgate end has its own ticket office. And so suddenly Moorgate had become highly valuable. And it very nearly looked like this, where just a single-story building standing in this highly valuable part of the city, which had been a real waste of some very highly valuable real estate. Crossrail had the idea, or the foresight, to have us look at where we could thread structure through, and Chris will take us through a bit about that, and to allow us to build a taller building over the top. And aren't we glad they did? You can see the same building at the bottom, but that V-shaped column there is supporting 1,000 highly paid bankers. And by allowing access on top of the station, it created a three-dimensional world where the pedestrianised street at the front, and then public space in the middle, and the building upstairs for the tenant. And by good fortune, this is an area of town where that is a highly relevant action, because the city works, this part of the city works at first floor podium, and the bridges crossing the roads, walkways crossing buildings, and all focused on the Barbican Arts Centre to the west. But the constraints at ground and first are completely blown away by the constraints below ground. There's 3 tube stations and several sidings running straight under the building. This is an image of the urban plan with the roof cut off, and we're looking down at the station. We're only able to put our piles down in the 2 pink areas to the top and bottom of that plan. Everywhere else is constrained by live rail. And if you break the circle line, it costs £1 million a day. So we were very careful. The constraints above ground, I've described in a bit, but obviously we took the site and extruded it as high as we could and then cut away to end up form-finding, rights to light to the Barbican, etc. All those models standing on our car park are different forms that you can see fill the same envelope. The most restrictive of these is a view of St. Paul's, where we're standing just behind the dome, Sod's Law, and a valley of a cut goes right through our building, so that from Westminster Pier, St. Paul's can still be seen in clear blue sky. And then a tenant came along, and actually all these decisions had led to a very fixed form, but it suited them very well. I mean, big dealer floors along the bottom, the size of football fields, all their public and open space in the middle. A little square to the south separates their wellness centre from the main building, and then stepping forms for all their different workplace environments and client-facing areas, give different west-facing roof gardens looking out across the city skyline. And it's just about finished. The public spaces are looking quite extraordinary. They'll be open in January, and you'll be able to go and use them. This unusual square, tripod square, above the main station and below the bank. You saw it from the front. The walkways have this artwork drawing people along it, bridges, stairs, gardens, and a little square designed by Andy Sturgeon. Well, when we put it all together, we're very lucky we had the very talented Robert Bird group, and you can see each grid line created a truss that was a different design to deal with the constraints of the space overhead and the location of the piles below. I have Chris Papanastasio here, director of Robert Bird Group. Chris has worked with me on 21 Moorfields for half his career, rising to be project director and last man standing. Chris's collaborative and inventive approach to engineering has driven the project forward and enhanced the design. Chris.
Thanks very much, Charles. So today I'm going to do a quick whip through of some of the structural challenges that we had to create a 100,000-ton building on top of a live underground station. So as Giles pointed out earlier, we have significant underground constraints within Moorgate Station. The presence of live running tracks, platforms, existing services, and existing foundations meant that we couldn't really put any foundations in the centre span of the station. This essentially meant that we had back-of-house areas to the north and south where we could negotiate pile locations. These were around 40 to 60 metres apart, or roughly the wingspan of a Boeing 737. The image on screen shows the 15 piles that we're using to support that building, and the Crossrail super pier built within Crossrail station. These piles are 1.8 and 2.5 metre diameter. They are 70 metres long, and they're the highest capacity piles asterisked in London, last time I checked. So once we knew how to create the capacity to build this building, we needed to understand how to build it. So going back to 2013, when the project was first looked at as a viability study with Landsec, we have a sketch there of a very simple piling grillage sat on top of Moorgate Station roof, and the biggest piling rig in the UK rumbling around on top. Effectively, the scheme looks a little bit different now, but we installed piles directly from the Moorgate Station roof. We put steel sleeves inside the station and spent 3 to 4 days constructing each pile. We needed a 3-day continuous pile test to prove their capacity, and this was all done without anyone really knowing within the station what was going on. Moving on to the superstructure. The superstructure is effectively a 17,000-ton steel frame spanning the width of a full-size football pitch. That's approximately 2.5 times the weight of the Eiffel Tower. As well as above and below ground constraints, we had significant logistical constraints for this site. We had a maximum crane lift of 16 tons, and we had a maximum delivery length of 16 meters due to local roads. This placed significant constraints on the structural solutions that we could adopt for the frame. So in order to transfer that span, 60 meters or so, we needed to look at various transfer systems, and we started off looking at kind of traditional truss systems, low-level truss systems. Due to the scale of the building, these were becoming extremely heavy, and they would have fouled the spaces at the lower levels of the building, really kind of ruining the architecture and not leaving much to coordinate plant and etc. in those spaces. We looked at taller arch systems. Now, these are great materially, but they require a lot of temporary works to build them. You need to support them on something until you've connected the arch, and we had a station with not very much load capacity on the roof. So the structural solution that we adopted harnessed the best of both of those systems. We incorporated permanent temporary launching trusses within the building, and we worked with Giles and the team to locate them and coordinate them. These trusses were lightweight and were only used to build the essential structure required to build up to the top of the arch. Once we were at the top of the arch and we connected the arches, we were able to run, or let the contractor run, with the rest of the steel frame, the concrete, the facade, the MEP fit-out. The early stages of the construction were essentially a race to the top of the arch. On the east side of the site, we have another very complex system where we need to cantilever out the building 25 meters over the crossrail box. The initial concepts for this east face truss were flawed in their number of bays and their structural efficiency, but we developed this concept of expressing structural load paths within the architecture. And through coordination with Giles and the team, we added the tripod that Giles mentioned earlier. Now, this tripod not only created the right number of bays to have a symmetrical system, but it also added stability to the structure and celebrated the support that we're gaining from the crossrail station. The final east face truss sits in front of the glazing line and is a celebration of the architecture and engineering that's gone into this building. That celebration continues internally with 25-meter spanning trusses supporting the Finsbury sightline setback. You walk past the tripod as you enter the building, and you walk through the launching trusses as you circulate in the lower levels of the building. You can see how the building was built above the station. And as you rise through the scenic lifts, you start seeing the arches appear on the floor plates, and you start seeing the bracing of the arches in the atrium. We worked and collaborated heavily with Giles and his team, but also with the steel fabricator on these systems. It was a really fantastic experience. And lastly, before I hand to David, we talk about movement. So the east building is essentially a floating building on top of cantilevering piles. It sways around 40 millimeters during a wind event and deflects up to 100 mil in full occupancy. The Moorgate station roof below is relatively rigid, and that supports all of the plant systems and all of the west buildings shown there in blue. All of the fire compartments, the MEP, the facades needed to accommodate these differential movements, particularly challenging for fire compartments. We developed a construction stage model to look at detailed movements pre-construction. We took information from monitoring points on site and fed it back into our construction model so we could feed back to facade contractors tolerances for fit-up. And lastly, the east facade, it's exposed thermally to the sun's heat and the cold. It expands and contracts up to about 40 millimeters. This was another complexity that David and his team needed to deal with in the facades.
Thank you, Chris. My next speaker is David Perez, Senior Envelope Design Manager at BAM Construction. David led the facade with me while at Wilkinson Air for 5 years, from concept through procurement to construction, and when he felt it was a stage he thought we could manage without him, he took his dream job as head of facades for BAM. David.
Thank you. I think after having heard the presentations by Giles and Chris, it's probably clear by now that 21 Moorfields is not a standard type of building. It's above a non-standard type of site and definitely has a non-standard type of structure. And I believe that understanding the nature of that structure is probably key to understanding the nature of the facade design and its complexity. So we go back to the color-coded diagram that Chris was talking about before, showing how the building moves in its different parts. I think this diagram probably is also useful to show how the facades in the building can be grouped. So we would have a first and predominant group of facades associated to the main building in red that moves, as Chris mentioned before, in all directions quite a bit. Then we'd have a second group of facades associated to the static structure at the base, the podium in blue. And then in between we'd have an interface facade that is meant to manage the movements of the building above. So I'll first talk about the first group of facades associated to the main building. This is mainly a group of curtain walls, generally in glass, but also in aluminum, with an aspiration for clarity, transparency, and lightness. And basically, they are the core of the main building. And I'll speak about 3 specific facades within this group. First, the east face truss, this east face truss facade, the main facade behind the truss that Giles and Chris had described before. In this facade, the truss and the facade act as one combined element. They dominate the east elevation, and they share a common design and performance. So on the one hand, we have the truss, which is acting as an active solar protection device for the facade, and on the other hand, the facade itself is engaged in all the movements related to deflection and thermal expansion of the external steel elements. One of the biggest challenges of this facade was its installation. So we have 250 mil deep glazed panels, sometimes 5 meters by 3, that had to be introduced in a 300 mil gap, basically 50 mil of wiggle room between the truss and the slabs, and slotted down through that gap from level 11 all the way down to their position, and manipulated from the outside through the openings in the truss. Every structural penetration includes thermal breaks to ameliorate the potential thermal breach. And the external face of the connection is concealed laterally by 2 continuous stainless steel closures with the purpose of visually detaching the truss from the glazing. In a way, the truss appears as it is floating in front of the glass of the facade. This dialogue between facade and structure was adopted as the narrative that drove the design of the facades across the whole building. The second facade in this first group is the crown facade, which is set above the one I just described, set back and inclined both in plan and section. It's actually a combination of 2 facades that have to look like one. This is mainly because the facade spans across 2 very different types of floors. Below we have the executive office spaces, the most exclusive office space in the building. All the CEOs will have wonderful views of the City of London. These floors include a closed cavity facade to improve the efficiency of the floor space. And above these floors, we have double height, massive mechanical plant rooms, single glazing and open to the sky above. So one way we used to kind of achieve that consistency, that visual consistency across the levels, was including an Antilio reflective coating on the outer pane of the glass of both facade types to increase the reflectivity of the glass without completely obscuring the transparency. Through samples and mock-up test units in Gardner's facilities in Germany, we finally reached the kind of fine-tuned balance between transparency and reflection. And this is an image showing the final result on the building, where you can see also how the facade had to deal with 2 different sort of interfaces. Internally, had to deal with a 1.5 meter planning grid, and the partitions of those offices could reach any one of those points, whereas externally, the facade had to respond to the 3 meter module of the predominant in the external facade. To do this, we introduced an additional mullion inside the CCF panel. And you can also see in this image the vertical recesses in stainless steel reflecting the internal structure, again, kind of creating that dialogue between structure and facade. And on the right, you can see an image of both facades above each other, forming the dominating east elevation seen from Finsbury Circus. And the third and final facade of this group is the west facade, where the rules of dialogue between facade and structure are somewhat inverted. Instead of having a projecting clear structure to the outside of the building, here the geometry of the diagrid is recessed into the facade with a metallic feature, with darker colors to relate to the palette that you find on the Barbican across the road. And in between east and west, the building's geometry has to accommodate all those constraints that Giles was talking about before. And as a result, we end up with a very complex set of interlocking volumes, inclined facades, faceted roof lights, internal glazed atria, and terracing levels that scale the building down towards Barbican. Second group is the podium cladding, which is considered as a heavy base to the building, anchoring the building to the ground. Here, the materials used are dense and heavy to provide the podium with its density and weight. And we find stones for floors and walls, metal panels and GRC for soffits, metal louvers, and most importantly, a whole set of very large precast panels that cover 3 elevations of the podium. Emerging from the west end of the podium, we find the amenities building, which includes these perforated metal skin that shows a sequence of diagonal folds, which relate back to the geometry of the diagrade on the west building, on the west facade of the east building. Again, giving a hint of that dialogue between facade and structure once again. And the third and final group is what I've nicknamed pivoting facades, mainly because these facades are meant to, among other things, accommodate the movements of the building above, and they do that through their pivoting action. The zigzag layout of the facade and the fins behind stabilize the facade and provide restraint to the lateral loads. The bottom brackets allow a sway of the facade at the top of up to 40 mil in every direction, and the top brackets allow for a vertical movement of 100 millimeters or so. And the image on the left shows just how difficult and what a challenge it was to install these enormous panels in place with what I hear is the only manipulator in the country that can do that. And here's an image of the facade installed in the building, very recent image. And here a more holistic view of an example of one of each of those 3 families that I've just described above each other, working as a system. Whoop, that wasn't me.
Oh, sorry, probably me.
Yeah, so yeah, the 3 facades above each other forming a system.
Thank you, David. Can you move the slide on one, please? Our final speaker is Shane Ensel, Project Director for Construction for 21 Moorfields at Landsec. Originally from Brisbane, Shane has worked his way across Asia, building several skyscrapers and arriving in London 29 years ago, and working on the Shard and the Scalpel. He's led 21 Moorfields since we moved into construction, overseeing it from the piles to the completion. When I met Shane 5 years ago, he told me he was a bulldozer and he just kept moving forward until the job is done. How's that going for you, Shane?
Thank you, Giles. It's 22 years I've been here, not 29,
Sorry.
But that's fine. I started on this in 2017. One of the 2 project directors for Landsec who have gone through the whole build cycle on this. This is definitely the most complicated thing I've done anywhere. You've heard about some London projects, but I've done the Olympics and the Commonwealth Games as well, so nothing comes anywhere near this, particularly as a commercial office block. The demolition of the original buildings was pretty simple. It was just a traditional masonry building knocked down. All we had to do was make sure we didn't tip anything down into the station or put too much dust in there. The next picture just beside it just shows you the scale of the piling deck and everything we put on. The biggest challenge to this whole project really was the creating the openings through the retained deck into the station. So this is some photos down below. You'll see there's pipes and wires and cables running everywhere. TfL generally don't know where they start, where they finish, or what they do. Also, we uncovered a lot of other problems. There's multiple train stations in here. Bits of equipment have been placed all over these areas for different train lines without anyone knowing. So when we tried to track and trace everything to take this stuff out of the way, it was an absolute nightmare. TfL is basically a big cumbersome beast that moves at glacial speed. I'm sure some of you in here have dealt with them. It doesn't sit very well with us. We were quite lucky we didn't end up with a very good person at TfL and a very good TfL contractor, Dellerton. We managed to get the services cleared 17 minutes before 8 o'clock on the last day, before there was an automatic extension of time for Mace digging the piles. It's been an absolute joy dealing with them, and to this day I'm still trying to close out with them. So, yeah, TfL, there you go. Procurement's always been the main driver for this project. what we decided to do is we thought we'd do something different. We decided we'd go into PCSAs with these 4 main contractors, and we'd take the design through and try and get ourselves to a fixed price lump sum and an agreed program before the piling finished, which is when we were going to go to the market and get ourselves our main builder. The big upside of this is we kept control of the process, and we managed to design, procure, fabricate, and deliver the steel to site 1 week after we agreed the main contract sum. Yeah, so this just shows you how massive it is. That's just one piece. The site itself is very, very constrained. We have built up to the boundary on all sides, maximised out this as much as we could. It became very challenging for McAlpines to actually provide site establishment for the guys on site. We capped out at about 1,000 guys per day. So the accommodation was moved around the building as it progressed and then off-site. So, COVID hit us pretty badly. At the time we were in the middle of doing the steel structure. The guidance that came out, as you're probably all well aware, was social distancing. One person had to do a job on their own. So basically we were bolting up structures. It delayed us for 3 months and we had no chance to get that back. The other thing at the time was Brexit. We did do a lot of pre-planning on Brexit with the supply chain. To be honest, it didn't really affect us. We had contingency plans for storage of materials in the UK, but we had virtually no real delays on the job from that point of view. So I just want to leave a couple of parting thoughts for people being a property developer, but this building I think will be here for 120 years. It's been absolutely maxed out on the site. I don't know who would ever try and pull it down. And if you did try to pull it down, I don't know who would have the appetite to spend years negotiating with TfL to try and actually do it. And anyone who wants to try, good luck. Thank you.
Thank you.
Thank you very much, team. So thank you very much for your presentations. Giles, that's been fascinating, and it's obviously been a massive and an amazing project. And thank you very much for your presentations, all 4 of you. We are soon going to be taking a break, but could I just first of all thank all of our speakers. So please, another round of applause for all of our speakers this afternoon. And I'd like to just introduce, so we are going to have a break, and the break will be, it's a 30-minute break, so you will have a 30-minute break.